Section 1.2 Some Principles of Quantum Mechanics. In quantum mechanics, particles are waves, waves are particles. Energy is quantized. For example, in a hydrogen atom, both the nucleus and the electron are waves. The electron is lighter and thus is more wave-like than the nucleus. Photons are particles, and a light wave consists of photons. Energy is quantized. The atomic orbital energy levels in the hydrogen atom is quantized. It has to be -1/2n squared. And n is an integer. Now let's look at the shapes of the waves of the particles. They're also called the probability waves. The shapes of these waves are governed by this time-dependent Schrodinger equation. H psi is equal to I h bar times the first derivative of psi with respect to time. This H, Hamiltonian, is the total energy operator. Its physical meaning is the total energy of the particle. This psi is the wave function of the particle. It tells you the shape of the wave. I is the square root of -1. I squared is -1. H bar is the reduced Planck constant. H bar is equal to h over 2 pi. And over here, t is time. This tells you how the wave function evolves with time. If the wave function is independent of time, we have h psi is equal to E psi. This E is the energy of the particle. For a three-dimensional particle or wave, because of the wave-particle duality, we have this h is equal to negative h bar squared over 2m. This is the mass of the particle, and this are the second derivatives. The v here is the potential energy of the particle. So all you need to do is to plug this expression in here, and then solve this Schrodinger equation. You will be able to find some wave functions that satisfy this condition. When you apply this h to the wave function, you will get this original wave function back multiplied by a constant. That constant E is the energy of the particle. Now let's look at this. This is the potential energy of the particle, and the h corresponds to the total energy of the particle. So you might have guessed that this is the kinetic energy of the particle in the x direction, y direction, and z direction. Now let's look at some waves. So this purple curve is a wave. Over here you have positive sign. Over here you have negative sign. In the middle you have a node. So this is a node. Positive, negative, a node in the middle. A wave function has no physical meaning. The wave function squared is the so-called probability density. So we know what probability is. Probability density is the probability per unit volume. For example, I'm sitting in my office. The probability density of me is 100% of finding me in the office divided by the total volume of the office. That's the average probability density of me in the office. The probability density is psi squared, wave function squared. Therefore, it's always positive, except at the node. It's also 0. When psi is 0, psi squared is also 0. When you see psi is equal to 0, that means there's no chance for finding the particle at the position. That's why in the atomic orbitals, we sometimes see nodal surfaces. Now let's look at the constructive and destructive interference of waves. Let's say wave 1 and wave 2 are in phase. And then we combine these two waves, we have a bigger wave. That's constructive interference. We can sometimes observe the cancellation between two waves. Wave 1 and wave 2 are out of phase with different magnitude. Therefore, they cancel but not completely cancel. The resulting wave is this, the red one.